Bond energies. All right, this is a second way we could do these. All right, I've done energies using this equation. All right, we've done energies using delta H of a reaction equals delta H of the products minus delta H of the reactants. See, as soon as I start recording, things go wrong. Okay. All right. Now, we've done this before using the delta. Now, look, here's why this worked. The delta, I need you to listen to this because this is going to be the exact opposite. It's not going to make sense to you. All right. Products minus reactants worked, and I explained that with Hess's law, because these were delta H's of formation. That's what that little zero above means. It's the delta H of formation. So the delta H of formation, I have to keep the products the same sign, so there's no negative sign in front of him. And the reactants get this negative sign. Why? Because I got to change the sign of the reactants. They're not being formed. They're being broken up. So if I have like A, B plus C, D yields X, Y plus, I ran out of letters. Either way, these guys, the reactants are being broken up. All right? And that's why the delta H of formation, that value, is going to be the exact opposite. Well, for this one, the amount of energy required to break a bond, who's being broken? The reactants are being broken, so they keep their same sign. It's the products that get the opposite sign. So here's what this equation looks like. Delta H of the reaction equals a reactants minus products.
The hardest part about this is going to be trying to keep everything together.
I know. Well, I purposely I would save this for last, because if you look at all our other equations, they're all products minus reactants for delta S, delta H, and delta G. But for this guy, for the bond energies, there'll only be one on the test that's going to ask you to do this. It's going to be reactants minus products. All right. There are some weird things that happen here. You might say, well, this is not too bad. I told you it's only going to take me 10 or 15 minutes to explain this. Well, there are some weird things. So I want to do one example here, and then I want to point out one example from the homework. Actually, kind of do it, set it up at least for you. All right. Try this guy right here. Br2 plus 3F2 yields 2BrF3. There's something weird about the reactants. You can't do what you did in necessarily what you did in the previous ones. Because here we're talking about each individual bond, not the actual compound. And that's a little strange. Let me show you. You all have that chart in front of you on page 6, what is it? I say 610? 610? Yeah. You look at that chart on page 610. Let's try to get the first one. Who am I looking up? First, again, you have to do this in the test. Delta H of the reaction equals delta H of what? Reactants minus delta H of the products. Okay. Now, who am I going to look up first this time?
The left.
Yeah, exactly. The reactants. Bromine. Look up bromine. See if you can find them using that chart. Because it's important to know how to use that chart. Notice it looks like it's only half the chart. Why is there only half the chart there? Can anybody figure that out? Why they only have half the chart?
Because all the numbers are going to be the same.
Yeah, you would just be doubling it if you had the other half. You see what I'm saying?
We would show. Yes, like 15.
They'd be like, yeah, exactly. So find BR and BR, and what do you get?
193.
Everybody get 193?
Yeah.
All right. So 193, and is that what are the units for that? What does it say they are?
Kilojoules per mole.
Okay, so kilojoules per mole. All right. What else do we have? It's also a reactant. This guy right here, right? So I have plus. What do I have to do? How many fluorine bonds are there here?
6.
No.
3.
3 times the fluorine bond. If I were to draw it out, would look like this: F F. The bromine bond would be Br Br. Something weird is going to happen in the next one. You'll see. So 3 times what's fluorine's?
155.
All right, minus. This is where it's weird. You would probably think to yourself, minus, okay, 2 times whatever Br and F is. But that's not correct. Because if I were to draw out, now everybody watch this, if I were to draw out the BrF3 molecule, the only way you could draw that, all right, would be like this. How many BrF bonds are in that molecule? 3. And I have 2 of those molecules. So how many total bonds do I have? I'm actually multiplying not by 2, but by 6 here. Mm-hmm. And what is the BrF bond? Again, why is it 6?
249.
249? Okay. Well, let's finish it up, and then I'll show you some other examples of guys like that. Kilojoules per mole. All right. Now, since you're multiplying by how many moles you have, the moles are going to cancel. You're going to left with just kilojoules. What do you get? Do that math for that and see what we get for our answer. Negative 836? Do y'all get that? Make sure you all get that. You're doing it right. I don't know if that's right.
Negative 836.
And if it's negative 836, you can still tell me the same answers I could have asked you on the previous ones. Is it endo or exothermic? Exo, because it is negative. Is it feel hot or cold? Most likely. Hot. Is it releasing or absorbing energy? Releasing. Okay. Is it favoring spontaneity or not?
Yeah.
Favoring, because it's negative and it's delta H. All right, even though it's a delta H calculated a different way. All right, now, I told you I want you to open up your book. That's it for the notes. I have nothing new to put in for notes, and it just fit probably in your space you had there. But open up to page 639, which you erased. And
I don't know what you're talking about.
I really don't know.
let's look at some other examples of this that we have to be careful of. All right? Watch.
Oh, what page? 639.
639.
I'm pretty sure you didn't write it up.
Okay? Let's take a look. I believe I had you guys do numbers 46 to 49 or something like that, or 45 through 49. Anyway, let's look at some guys like 46A. We have a problem with 46A. You're told you have a double bonded carbon. And since I would recommend kind of drawing these out as you would have drawn them out almost in organic. All right? Here's what you would have to do for that guy. You got a compound like that. You're going to have to look up how many different things here. You're going to have to look up 1, 2, 3, 4 CH bonds. 4 times whatever the CH bond is, right? Where are you going to find that? Same chart you've been using, right? But you've got a double bond for this guy.
So 2 times.
No, it's different than that. Turn back to 610 and look at the bottom of that page. Double bonds have a special energy associated with them.
836. I remember.
So you would have one, you see it there? You'd have one at the very bottom, double bonded carbon. Okay? Yeah, you got to be careful with
So
those.
then what do you do? Like, just times
Just add
602.
So it would just be, yeah, plus whatever that bond, what was it, 602 you said?
Yeah.
All right, so it'll be, if that will be that compound. And then plus whatever other reactant you have. Let's see the other reactant of that one. Bromine. Well, that's an easy one, right? But how about a guy like BrH2C? What's BrH2C going to look like?
It's a good question.
It's going to be,
So it'd be
4 times.
It'll be
Eight,
just 2
eight.
C's. That's one compound.
Yeah, that's all in one compound. Oh, no, I'm sorry. BrH2C, CH2Br. You have to draw it out again. So here you go. C, Br, and there was a Br in this one too, right? So again, how many carbons and hydrogens would you have? 4. How many CBr bonds would you have? 2. And how many? This is just a CC bond, so you could just use the one from the chart. So you'd have 3 different things add up there. See what I'm saying? It's a pain in the neck.
It's whack.
Mm-hmm.
That's for BrH2